Hello engineers, welcome back. In this video, we're going to practice the concept of backtracking with the help of another lead code question. Okay? Hope you're ready. Let's get started. So this is a question we're going to look at today. It's called permutations. So let's first try to understand the question and then see how we can apply the backtracking framework to this problem, right? So given an array nums of distinct integers, return all the possible permutations. You can return the answer in any order, right? So let's see what it means. So if this is the array 1, 2, 3, we need to return these permutations. So if you look at it closely, we are holding 1 in its place and swapping the remaining 2. 2, 3 is here and 3, 2 is here. So this is one set. And then we are starting with 2 and then swapping 1, 3 and 3, 1. This is another set. And then we are starting with 3 and then we are swapping 1 and 2. 3, 1, 2 and 3, 2, 1. So these are the permutations. So let's understand this concept. So if this is the array, so how do we build a permutation? There are 3 spots. To build the first spot, we have 3 choices. We can either fill it with 1 or 2 or 3. There are 3 choices. And to fill the second spot, we will be left with 2 choices. And to fill the third spot, we will be left with 1 choice. So a total of 6 is essentially 3 factorial. We will have 6 different permutations for a given array of size 3, right? So if I fill the first position with 1, I can fill the second position with either 2 or 3. If I fill it with 2, I can only fill the third one with 3. If I fill it with 3, I can only fill the third one with 2. So that's how permutations work. Okay. So if we draw a tree, we can visualize this easily. So if this is my tree, what do we need? We have 3 choices to fill the first position. These are my 3 choices to fill the first position, and I have first position here. To fill the second position, I have 2 choices. I can fill it with 2 or I can fill it with 3. If I fill it with 2, my permutation will look like this. If I fill it with 3, my permutation will look like this, 1, 3, 2. Right? Similarly, if I start with 2, I have 2 choices for filling the permutation, one with 1, another with 3. If I fill it with 1, it will become 2, 1, 3. If I fill the second position with 3, it will become 2, 3, 1. Similarly for the third one, let's quickly do it. I'm filling the first position with 3. I'll be left with 2 choices. For the second position, I have 2 choices. So what is it? 1 and 2. If I choose 1, then my answer will be 3, 1, 2. If I choose 2, then my answer will be 3, 2, 1. See, to fill the first position, we had 3 choices, right? These are my 3 choices. To fill the second position, there were always 2 choices. 2 here, 2 here, 2 here. To fill the third position, there was only 1 choice. 1, 1, 1, 1, 1, 1. Okay. So that's how the concept of permutations work. Okay. Now let's see how we can apply the concept of backtracking to this. So let's look at it closely. What do we need? We are making the first move. This is our first move where we are choosing one path. We are choosing to go down the path of the first position being 1. Inside the path of 1, we are again making another move where we are choosing the second position. Okay. Again, here there is a choice. So here again there is a move. Right. In this move, there was nothing to do. It was straightforward selection of the next available element. But here we are making a swap. Right. We have swapped these 2 positions. So it was originally 2, 3. Now it became 3, 2. And then when we go back up here, we need to start our next move here. In order to start our next move, we need to retrace back to our original state, and then we can start our next move and repeat the process. And once we reach here, we go back again and we restart the third move. So these are my moves, right? So you can see the pattern. We are going down one path, reaching the end, coming back up and restarting, right? So we can directly use the concept of backtracking here. So how can we do that? What is the concept of backtracking? The framework. We make a move, we call recursion on remaining moves. We undo the last move and redo recursion on remaining, right? So this is what we discussed in our previous video as well, where we were discussing introduction to backtracking. So this is what we are going to do. Okay. So what are our moves? First, we make a move down this path, and then we reach the end. We undo this move and redo with the remaining moves, right? So what is the move that we are doing? When we are going down this path, we are making a swap with itself, swap itself. And when we are going the right subtree, we are swapping the remaining elements. Swap remaining. Okay. So let's see. Let's try to code it first, and then we will trace it so that it will be more clear. So first, let's create our function. So let's call it void backtrack. Let's call it backtrack. And for this, we are going to take our main input vector as it is by address. And then we are going to take an index to start with. And then we're going to take an index called next to make the next moves, right? So let's start with the base case. What will be the base case? As we can see here, once we reach the depth, here is my permutation. So this is my base case, right? So I'm traveling down the path, one path. If I hit the base case, I add it to my list. If I go back and start a new path, if I hit the base case, I will add these to the list and so on. So we need to keep track of a result vector as well. So this is what we are going to return. This will be vector of int by address, and let's call it result. Okay. So let's pass all this. Let's create our result vector of int result, and let's start giving these values. We are passing the main vector, we are passing the result vector, and we will pass our index and next. Both are 0 at this point. Okay. So let's write our base case. Our base case is if index reaches the base, which is nums.size, we can directly add, we'll return from here of course, but before returning we will add this to our result. We will add result dot pushback nums. So in our case, we are directly altering the nums. Okay, we are making use of this nums directly without having to use any additional space. So we are directly altering it, going down this path, altering it, and then returning it to the original state, and then going down a different path. Okay. So if this is the base case, so what is my first move? Make a move. We are making a move called swap. Swap nums of index with nums of next. Initially, index and next are 0, 0. So we are swapping with itself. Now we can call the recursion. So recursion is backtrack nums result and then we need to call recursion on the next moves, right? So we will call index plus 1 and index plus 1 on this as well. So for this path we are calling index plus 1 index plus 1, so that we will finish this path, and then once we are done we need to undo, right? So this is undo. For undo we do the same thing, we swap it back, we return it to the original state and then redo with remaining moves. So what do? We call recursion again with the remaining moves. So for this we will pass our index as it is and we will increment our next, and that's it. Okay, so now we can return our result. Okay, so this is how we have applied the framework. We will trace it so that it is more clear, but let's run it and see. Spelling mistake somewhere. Where? We missed another case where next, we are also keeping track of next, right? Next can go beyond. Next also need to be checked. Nums dot size, and we return. Okay, now the solution is accepted. Okay, now let's try to understand what's going on here. So the concept is the same. We are making a move, we are doing recursion, we are undoing the move and doing recursion on the next steps, right? So let's see how this pans out. So what are our trackers? We are here originally 1 2 3, where our index was 0 and our next was 0, right? This was our start position, and then we started to make our first move. So what did we say? We said swap nums index with nums of next. Here both index and next are same, so we are making a swap, self swap, no problem. And then we are calling recursion on index plus 1 index plus 1, right? So I is now 1, n is now 1, and if we go down this path, what will happen to nums? So we called recursion again, we are again back to this position, swap. Here again both elements are same, so we are swapping the first index now, and then we are calling recursion again on index plus 1 index plus 1. So we go down this path again, this time I equals to n equals 2, and let's see what's happening in nums. In nums again we have reached this position where we are swapping 2 with 2, so we are swapping this position. It is a self swap, so nothing to change. And then we call recursion again on index plus 1 index plus 1. So we are going down this path, I equal to 3, n equal to 3, and then let's see what is happening at nums. So we have reached here where I equal to 3, n equal to 3, right? So this is where we hit the base case. Our index has reached the size. So this is our base case. So we will add this to our result and return. So return, let's use another color. This is my return. So I have come back here. I went backtracking and then I have returned from here. Now what do I need to do? I need to undo the swap. So undo is happening here. Since it is the same index, nothing to swap, the array remains the same. But after swapping, what do? Redo with remaining moves. Let's see how this looks like. What am I saying here? Redo with remaining moves. I am saying index and next plus 1. So index will remain the same, I is 2. Next will become next plus 1. So n will become 3. And let's see what is happening to nums. Nums is currently 1, 2, 3. And because n is 3, this is our second case. Because n is 3, we have to return from here. So there is no path forward. So we have to return from here. Okay. So we found our first permutation, and then we checked if there is anything else. There is nothing else. So from here we will return. So we go back to the parent. So this left subtree is completed now. Now we will do the right subtree. So for right subtree, what do we do? So we repeat the process, right? So we undo the swap. Once we return, we undo the swap. So this is undo. And then we call recursion on the remaining moves. So what are my remaining moves? Index and next plus 1. So index remains the same, I equal to 1. N will become 2. Let's see what is happening inside nums. So it was like this. Now we call recursion again. Now first move in the recursion is swap, right? This is where swapping starts. Swap index 1 with 2. So swap these two. Okay. So let's swap them. So this is becoming 3 and then this is becoming 2. So you can imagine it like this. So we made a choice, we came down the path of 1, and for the second position we made a choice, we went down the path of 2 and finished that permutation. Now we are making a choice of filling the second position with 3, right? And then now we'll go down this path. Let's see what happens. So for the left subtree, what were we doing? For the left subtree, we were doing index plus 1, index plus 1, right? So I will become 2, n will also become 2 because it is index plus 1, index plus 1. And what is happening to nums? Nums will remain as it is because now it is a self swap. 2 is 2. Okay. So this is the swap. Nothing to change. And then it will continue further where I will become 3, n will become 3, and this will remain as it is. Now we have hit our base case again. So we can add this to our result and we return. So when we return, we undo the swap. This is undo, and then we call recursion again. So what do we call recursion on? We call recursion on index and next plus 1. So index is 2, n has become 3 now, so this is a dead end. Okay, so we are done with this path. Now we can directly return to our parent, which is here, right here. This is my parent. So is there anything else left to do here? Yes, we just need to do one more check. We go down this path, we need to do the right subtree for this guy. It is a simple one. We go down this path where I will remain the same, but n is 3 now because we are doing n plus 1. Or before that we need to undo the swap, right? We need to undo the swap, so let's do that. So we will undo the swap. So now my nums has become 1, 2, 3 again. We have undone it. Now it has become 1, 2, 3 again, and we go down this path. N is hitting 3, so this is a dead end. So we return. So we return here all the way back from here. Okay, so we are done with the path of choosing 1 as the first position. Now we will go down the path of doing 2. Let's see how that goes. Let's draw it separately. So we are going down this path now. So currently our nums is 1, 2, 3. Now our I is 0, n is 0. Okay, so we are done with the left subtree. So we are calling on the right subtree. So what is the right subtree? index and next plus 1. So I will become 0, n will become 1, and now here we have a swap. So it is 1 to 3 currently. Now we need to swap 0 with 1, right? So let's swap. So now this has become 2 comma 1 comma 3, and then the process repeats. So for the left subtree we do I plus 1 n plus 1, I equal to 1 n equal to 1, and no change. And we go down I equal to 2 n equal to 2, no change. I equal to 3 n equal to 3, no change. And we have hit our base case, so we will add 2 comma 1 comma 3 to our set. And then we do the right tree, where we keep I constant and we say I equal to 2 n equal to 3. We have hit our dead end. Okay, so we return, and then we go back here. So what is the position here? We have I equal to 1 n equal to 2, and here we have a swap. So what is the swap? So we were at 2 1 3. Now we need to swap 1 with 2, right? So we need to swap these two. So let's see how that goes. Now we have 2 3 1, 2 3 1. Next we go down the left route, we do I plus 1 and I plus 1 again, n is also 2, and no change. I equal to 3 n equal to 3, no change. And we have hit our base case, so we will add 2 comma 3 comma 1 to our result and return. So we return here, we do I equal to 2 n, I equal to 2 n equal to 3. We have hit a dead end, so we return. So this part is done. So one last check to do here, I equal to 1, n will become 3, and this is a dead end. So we return all the way back to here. So while returning, we always undo the swap, right? So we need to undo. So let's undo. This is one undo. So this has become now 213 again. 213. And we have returned here. Oops, the blue color. So we have returned here now. So we need to undo this as well. So now we have 1 2 3 back. Okay, and we go back all the way here. Now our third piece will start. So let's go all the way forward. So we are here where I is 0, n is 0. So again we start. What do? We keep I constant, I equal to 0, but we move n forward. Now n is 2. So there is a swap. Now it is currently 1 2 3. Now we need to swap 0 with 2, right? So let's do that. 1 with 3. So now 3 is in the first position and 1 is here. And then this process repeats, right? So yes, let's go down. So we do I plus 1 and n also I plus 1. So 1 1. So no change. So we go I equal to 2, n equal to 2, no change. I equal to 3, n equal to 3, no change. And we have hit our base case, and we will add 3 comma 2 comma 1 to our result. And then we return. We do I equal to 2, n equal to 3, and this is a dead end. So we return. We come here. We do I equal to 1, n equal to 2. So we have a swap here. So what is the swap? It was initially 3 2 1. Now it will become 3 1 2. We are swapping 1 with 2. Okay, let's do that. 3 2 1 will now become 3 1 2. Now let's go down this path. Now again, I equal to 2, n equal to 2, no change. And I equal to 3, n equal to 3, no change. And we have hit our base case. So we will add 3, comma 1, comma 2 to our result and we return. So here it becomes I equal to 2, n equal to 3, dead end. So we return. Here again it will become I equal to 1, n equal to 3, dead end, and we return all the way back. So while returning, we will obviously undo here, undo here, and we go back to our original state and we have our nums as it is, and then we return. Okay, so that was the full trace of our code, right? So we have successfully used the framework once again to solve our problem. So let's now discuss the time complexity, right? So as we have already seen, to make the first choice we have 3 options. To make the second choice we have 2 options. To make the third choice we have just 1 option, right? So that is essentially n factorial. So to go down one path, for one path it is n factorial, and there are 3 such paths, right? So if there are n such paths, we need to go down n times each path, and at every path the number of choices are reducing. So this will become the time complexity of all. Okay. So if this is complex, you can also do it with a for loop. You just need to remove this and use a for loop to keep track of text. Okay. Both ways, the time complexity would pretty much be the same. If you are comfortable with using for loop as a concept for backtracking, definitely go ahead and do that. Okay. So that's it for this video, guys. I hope you enjoyed solving it. Do attempt and see how backtracking flow works. If you have any questions, definitely ask me. Don't forget to like the video. Don't forget to bookmark the playlist so that you don't miss out on any future video. Don't forget to comment or if you have any questions or suggestions. And thank you so much for watching. I will see you in the next one. Yes.